And not only can we find lengths of curves, we can also find areas of surfaces. And we do surfaces of revolution, so we're taking a curve and revolving it about one or the other axis to make a surface. You've done volumes of revolution, it's the same idea, except now we're worried about the surface area. So we have to do a formula for the x-axis and a formula for the y-axis. And we're going to start with something which is quite classically simple, but really good to see. We're going to calculate the equation for the surface area of a sphere, which if you look up on the formula sheet, you'll find is 4 pi r squared. So that's what the answer should be, so it's always nice to know where we're heading. Okay, so how we're going to do it is we're going to think about rotating a circle about one of the axes. So if we draw a circle, yeah, it's actually a perfect circle because I'm going to label it as such, so that's the formula r squared equals x squared plus y squared, so that'll be at r, and that'll be at negative r, so I've labelled it as a circle, so it doesn't look like a circle, it's your eyes that are the problem, not my diagram, because it is a perfect circle. And I'm going to rotate it, doesn't really matter, I'm going to rotate it about the x-axis. Okay, so I'm really only interested in the positive part of the circle, so when I do the square root, I'm going to use in the positive root. So the positive part of the circle between r and negative r, rotated about the x-axis. Okay, so the formula I'm going to use is this top formula, which means I need an expression for y and an expression for dy by dx. So let's do a little bit of that work down the side here before we start. So rearranging that equation tells me that y equals the square root of r squared minus x squared. So I need that to put into the equation for y, and I also need dy by dx. So let's differentiate the sucker. So dy by dx, okay, that's effectively a half power, so I get a half r squared minus x squared to the negative a half times chain rule, inside derivative of the inside bit, negative 2x. So the half and the 2 can go out, I'm left with negative x over the square root of r squared minus x squared. Okay, so I now have expressions for both y and dy by dx. So the area of the curve, according to that formula I've got at the top, should be the integral. I'll just copy the formula down so we can see the whole thing. 2 pi y square root 1 plus the derivative squared dx. Okay, so that's our formula, and there's our pre-worked bits and pieces down the side here, so we should be able to just substitute everything in. So the area should equal the integral from negative r to r, 2 pi, I'll take that right out the front because I can't bother working with it. Y we know is square root of r squared minus x squared, square root of 1 plus the derivative, which is negative x on the square root, r squared minus x squared, and that whole thing is squared dx, which looks pretty entertaining. So let's have a go and see if we can simplify that down a little bit. So what have we got? We've got the 2 pi out the front. We've got the integral negative r to r. Not much I can do with that first bit at the moment. I think the bit that's going to be helpful is what's going on in here. So if I square that whole thing, I get x squared over r squared minus x squared. Let's make this a single fraction. So I've got 2 pi negative r to r square root r squared minus x squared, and in here I'm going to have r squared minus x squared. On the top I'm going to have r squared minus x squared plus x squared, which is just r squared. Those guys cancel out because it's under the square root. The square root of r squared is just r, so the whole thing is just 2 pi integral from negative r to r of r dx, which is pretty straightforward. So we're left with 2 pi, if I integrate this thing I get rx between negative r and r, which gives me 2 pi r squared minus negative r squared, which is 2r squared times 2 is 4r squared. So altogether I'm left with 4 pi r squared, which I do know is the surface area of a sphere. So the formula seems to work, which is always good.